So in the last lesson, we talked about a very, very general idea of what it means to approximate area under a curve, and we introduced it using distance traveled. So we were looking at a velocity function over a certain amount of time and basically used it to estimate, not get an exact value yet, but to estimate what the distance traveled would be by looking at a velocity function over a certain length of time. So we saw these, what I called perfect geometric shapes, rectangles, different sized rectangles, and then we looked at something that's not quite a perfect geometric shape and talked about how we could estimate the area under the curve using rectangles, because rectangles are obviously an area that's very, very easy for us to find. And then we talked about if you're looking at rectangles on the left-hand side, rectangles on the right-hand side, rectangles in the middle, how you can get the most accurate representation. All right, and then we learned this notation for right, left, and midpoint Riemann sum. Okay, so we are going to get a little bit more specific here. Rather than just looking at a picture, we're going to look at specific functions. All right, so we've got this whole little intro here that I'm basically just going to kind of read and explain. So assuming that f of x, like I said, this time we're going to be given a function, assuming it is a continuous non-negative function. It has to be continuous, otherwise we won't know what to do with the gaps in the graph, and for now it has to be non-negative. Not always, but for right now, since we're just introducing it, it needs to be non-negative. And then over an interval from a minus b, we're going to break it up into n equal intervals, so we might split it up into 8 rectangles or 6 rectangles. And then each subinterval would be b minus a divided by n units wide. So you do n point minus n point. The b minus a would be the width of the whole interval, and then if you're splitting it up into n intervals, then you divide by n to see how wide each one of the rectangles is. And then we are approximating area using rectangles. These rectangles are known, again, as Riemann sums. So here's the notation that we talked about yesterday. For example, R sub n means taking a right Riemann sum, cutting the interval into n subintervals. So we're going to find R4, L4, and M4 for this function. So kind of helpful to draw a picture so we know what x squared looks like. Very simple function here. So let's take x squared from -2 to +2. Okay, so at -2 and +2, our function is up at 4. Okay, so start with a point here and a point here, and then 1 and then 0 right here. Okay, so we're going to get just a very quick sketch of what our parabola is supposed to look like. So it looks like that. And remember, what we're trying to approximate is the area under the curve. Okay, so let's start with what R4 would look like. So R4 would be these right-hand rectangles, so using the right endpoint for each one. So I'm going to color code these for you guys. So using red for the R4, so we would use this right-hand height and turn that into a rectangle. Then we would use this right-hand height and turn that into a rectangle. For this one, we would use this right-hand height, so there isn't anything there. Then we would use this right-hand height for the last rectangle. So we're trying to approximate the area under the curve from here to here. You can see this isn't going to be the most phenomenal representation, but we're going to show it anyways. So R4. What we do is we add up the area of all of these rectangles. So here we use the right endpoint. So we're going from -2 to -1, which has a width of 1, and then a height of, we use this height, the right endpoint's height, which is 1, plus from here to here, another width of 1. And then this has a height of 0, because we use the right height. Plus, this third rectangle has another width of 1. This one has a height of 1. So another 1 by 1. Plus, and then finally, this last one has another width of 1, and this rectangle has a height of 4. So we've got 1 plus 0 plus 1 plus 4, so that is 6. Now there are typically no units here. We might see an example in the future where there are units, but for now, nothing. All right, next one, we've got the L4. L4, I'm going to color code again. For each one of these rectangles, we're going to use the left endpoint. So for this one, for instance, we use this endpoint. For this next one, we use the left endpoint, so we've got this rectangle. For the third one, we use the left endpoint, which means we've got no height at all. And then for this one, we use the left endpoint. So that's our last rectangle there. So this is actually going to end up being the same area. So for this first rectangle on the left, width of 1, height of 4, because we use the left endpoint as our height, plus the second one, width of 1, height of 1, plus third one, width of 1, height of 0, and then plus for the last one, width of 1, height of 1. So this is again 4 plus 1 plus 1. So this one gives us 6 as well. So then for the midpoint typically is our most accurate. Not every single time, but typically it will be our most accurate. So for each one of these rectangles, not -2, not -1, we actually use the value at 1.5. So this will be our rectangle here. And here we use at -1/2. So there's our rectangle. This one we use +1/2. And then for this one we use 1.5. Okay, so again, 4 rectangles. I know it's getting a little confusing with all those boxes, but the midpoint with 4 subintervals. For this first one right here, width of 1, they all have a width of 1 because we split it up into 4 equal subintervals. This one is the height at -1.5. So if we were to plug -1.5 in there and square it, this is -3/2. So if we square it, we get 9/4. Plus in the next one, -1/2, we square that, we get 1/4 as the height. Plus, for this one, this is the same rectangle, width of 1, height of 1/4, and this rectangle is the same as this one, so width of 1, height of 9/4. So we add all these fourths together, we've got 9/4, 1/4, 1/4, 9/4, ends up being 20/4, which is 5. All right, so 3 different ways to approximate this. The midpoint is going to be the most accurate. You can see if you're looking like here, this green one is way too big and this red one is way too small, and then it's the exact opposite over here. The midpoint kind of balances out, but these are your 3 answers right here, R4, L4, M4. Here we're going to do the same thing for example 5, except this time we're only going to use one approximation. So L6, the left Riemann sum for this function on this interval. So what I'm going to start us off by doing is figuring out what the width of each one would be. So if we're trying to figure out the width of each rectangle, you do right endpoint minus left endpoint over the number of rectangles, and the number of rectangles is 6. So each one of them is going to have a width of 1/3. So that's not on the screen. There we go. Okay, so we've got 6 different subintervals. First we have the interval from 1 to 1 1/3. Then from 1 1/3 to 1 2/3, from 1 2/3 to 2, oops, I don't know why I made that open, from 2 to 2 1/3, from 2 1/3 to 2 2/3, and then finally from 2 2/3 to 3. So we've got the 6 different subintervals that were mentioned right here. So for the left Riemann sum, we use the height of the left endpoint. Okay, so we want the function value, basically. So if we want L6, notice up here how like each one of the rectangles had a height or a width of 1. So instead of multiplying by 1 each time, we could have put it out front. Same thing here. Every single one of them is going to have a width of 1/3. So we can put the width out front and then just add the heights together. So the heights, it's going to be the function value at 1 plus, for this one, the function value at 4/3 plus the function value at 5/3. These are the heights that we're getting. It's just whatever the y value is, which is f of whatever. Plus the function value at 2, plus the function value at 7/3, and then finally plus the function value at 8/3. Okay, so these are all the different heights multiplied by the width. Now this is definitely a calculator problem once it gets down to it, and then you're always just going to give a 3 decimal point approximation. Okay, so we've got a number of options here. For the inspire, what we're going to do is, I'm going to show you guys on a calculator page. You can define a function. So if you hit menu, actions, then you can define. So we can define f of x as that function, the square root of 6x plus 2. Okay, it's also definitely possible to just do like square root of 6, plug in the 1, plus 2, like you can absolutely do it that way. Same with the 4/3, same with the 5/3. If we do it this way though, if you have an inspire, you can just do f of 1 f of 4/3, which means if you can define the function, you can just plug the whole chain in like this. Okay, so 1/3 out front, and then in parentheses, f of 1, that's an e. Let's try that again. F of 1 plus f of 4/3 plus f of 5/3 plus f of 2 plus f of 7/3 plus f of 8/3. Okay, so here's the width right here. And then 1, 2, 3, 4, 5, 6 rectangles. For the height, we're using the left endpoint. So for example, on the interval from 5/3 to 2, we're using the endpoint of 5/3. So if we get an approximation here, 3 decimal places would be 7.146. Okay, so what we just did is we approximated the area under this curve between 1 and 3. Just an approximation, not an exact value. Okay, for example 6, we're going to do the same thing. M5 on this interval right here, again from 1 to 3. So we're going from 1 to 3, and we are cutting it up into 5 different pieces. So that means each one of them has a width of 2/5. So our first interval goes from 1 to 1 2/5. And then from 7/5 to 9/5, from 9/5 to 11/5, and from 11/5 to 13/5, and from 13/5 to 15/5, which is 3. Okay, so 5 different intervals there. Now the midpoint means we want the halfway in between point. All right, so I'll show you how to set this up. So M5, every single one of them is going to have a width of 2/5, so we can just throw that out front. And then we want the function value at. This one, for instance, goes from 5/5 to 7/5. The midpoint would be 6/5. And then plus the midpoint here would be 8/5. Plus the midpoint here would be 10/5, which is 2. Midpoint here would be 12/5. Then finally the midpoint here would be 14/5. Okay, so depending on the calculator you have, I'm going to show you guys on the Inspire. If you've got, TI 84, 83, whatever, you can literally plug the whole function in. So let me show you how you do that, for instance, without defining. So you'd still put the 2/5 out front, but then in parentheses, you could plug things right into that function. So since it's just a natural log function, you could do natural log of 6/5 plus natural log of 8/5 plus natural log of 2 plus natural log of 12/5 plus natural log of 14/5. Okay, so you just plug it right in, get an approximation. It is about 1.300. Now here's the thing, with that 3-digit accuracy, you actually do need to put the 00 because they are important digits. We're just not including the 2. So for our approximation, especially on the AP test, you would need those zeros because it's not like the decimal stops at 1.3. Those 2 zeros are important for the approximation. Okay, so there's our first couple. Let's flip over. We are going to do this one together. There we go. Okay, so now R4. So we've done left, we've done midpoint, now we're going to do R4. So our width is endpoint minus endpoint over the number that we're dividing into. So each one has a width of 1/2. So let's write our 4 intervals. So from -1 to -1/2, from -1/2 to 0, from 0 to +1/2, and then from +1/2 to 1. So those are your 4 intervals. We are using the right endpoint since it's a right Riemann sum. So for R4, every single one of them has a width of 1/2, so we put that out front. And then in parentheses, we're putting all of the heights. So it's basically like doing an area formula, just kind of in a compact way. So first we want the function value of, we use a -1/2 for this one, plus, then for the second block, we use the right endpoint, which is 0, plus for the third block, we use the right endpoint, which is 1/2, plus, and then finally we use 1. All right, so that can just go right into your calculator. Okay, let me show you the define thing one more time. So on the Inspire, you can define a function. We're going to type in f of x equals x squared plus x, and then just like the previous one, if you've got the 83 or 84, you can just type things right into your function. But this way is a little bit easier if you've got the technology for it. So put the 1/2 out front, and then in parentheses we've got the function value at -1/2. Oops, that was not right. Okay, open parentheses, at -1/2 plus the function value at 0 plus the function value at +1/2 plus the function value at 1. Okay, so it ends up being 5/4, exactly 5/4, or 1.25. So this, now there's a difference here. This is not an approximation. This comes out to be 1.25. We didn't have to round or anything like that. So with this one, you don't need the 0 because the decimal place stops at the 1.25 spot. All right, so we've got these other couple of examples. We are actually going to do these in class, these AP problems together. That way you can see exactly how a Riemann sum would pop up on the AP test. What you typically see is the table problem, and we've talked about a bunch of different types of free response problems that you'll see. Every time that you have a table, they will almost always ask you for a Riemann sum. So in class, we are going to talk about a free response example, and we are going to talk about a multiple choice example, but both very similar in that they involve a table. All right, so that's it.